Hello and welcome in a new video. We will solve now exercise 20. A particle moving on a parabolic curve of equation y equals 4t squared where x equals 2t. So we have a particle moving along this curve. So we have parametric equations. We have x and y as a function of time t. Question A. Determine the velocity and the acceleration of the particle at an instant t in the OX or Y system. So we need to find the velocity vector and the acceleration vector at time t. So we can write the position vector as it has two components, x along I and y along j. So x is equal to 2t and y is equal to 4t squared. Then we can deduce v. It also has two components. Vx is dx over dt, so it's equal to 2. And vy is equal to dy over dt, therefore it should be equal to 4 times 2t, so it's 8t. So the velocity vector is 2I plus 8t along j. And we can also find the acceleration vector. It's equal to dv over dt, so ax is 0 because vx is constant. And ay is equal to dvy over dt, so it's 8. Question B. Determine the normal an and tangential at components of the acceleration vector. So we need to find an and at. Now to find an, we have mainly two methods. The first one is to write it as v2 over rho along the normal unit vector, but here, since we don't have the radius of curvature rho, and since it's asked in the third question in part C, they asked the radius of curvature, then we will not use an equal v squared over rho. Okay, so we will deduce an from at and the total acceleration. Okay, so let's first start with the tangential acceleration. It's equal to at along tau. So we need to find what is at and what's tau. At is equal to d over dt of the magnitude of the velocity vector. So what is the magnitude of the velocity vector? It's equal to radical of 2 squared plus 8 squared t squared. So it's equal to this term. And we can take 4 as a common factor and keep it out of the derivation. So we will obtain 2 d over dt of radical of 1 plus 16t squared. Now we want to derive this quantity with respect to time. You can use this math rule. It says that d over dx of radical of f of x is equal to f prime of x over 2 radical of f of x. Here we have f of x equal 1 plus 16t squared. Therefore, at will be equal to f prime of x. So it's 16 times 2t, and don't forget this 2 here, over 2 radical of f, over 2 radical of f, and you will find at as 32t over radical of 1 plus 16t squared. So this is at, but what is tau, the tangential unit vector? So tau, we know that tau is equal to vector v over the magnitude of vector v. Why? Because simply vector v can be written as its magnitude times tau, okay? Because the velocity vector is tangential to the... So we can deduce the tangential unit vector So it's vector v over the magnitude of v. We have vector v, it's 2I plus 8tj, and we have the magnitude of the velocity vector. We have already calculated it, so it's this term, radical of 1 plus 16t squared times 2. And finally we can get the coordinates of the tangential unit vectors expressed on the Cartesian coordinate system. Finally, we can deduce AT, so vector AT will be equal to the magnitude of AT, which is equal to A dot tau along the tangential unit vector. Okay, you have AT and you have tau. You have just to copy the expression to find the expression of AT. Now AN can be deduced from the total acceleration vector and from the tangential acceleration vector. So AN is equal to A total minus A tangential. Do we have A total? Yes, we do. It's 0 along I plus 8 along J. So we can simply deduce AN as a vector, and we can also deduce the magnitude of the normal acceleration. Part C, deduce the radius of curvature of the trajectory at any instant t. So once we have AN, we can easily find rho, because AN is equal to V squared over rho. So rho will be equal to V squared over AN. We have V, and we can get the expression of the radius of curvature. Let's continue with exercise 21. The position of a particle M is specified in polar coordinates by r of t equal 2 sine t and theta of t equals t. So we are working here in polar coordinates, and we have a parametric equations relating r to t and theta to t. Question A, find the components radial and orthoradial of the speed v. So we need to find Vr and V theta, given that we have r and theta. So we have to prepare the derivatives. You can start doing r dot and theta dot, and also r double dot and theta double dot, because you will be asked to find the acceleration in question C. Okay, so we can directly apply the rule V equal r dot er plus r theta dot e theta. So what is r dot? It's equal to 2 cosine t. And what is, we have r. What is theta dot? Theta dot is equal to 1. So we can easily deduce V as 2 cosine t er plus 2 sine t along e theta. So Vr is equal to 2 cosine t. It's the radial component of the velocity vector, and V theta is equal to 2 sine t. It's the orthoradial component of the velocity vector. Question B, deduce the magnitude of the instantaneous speed. It's simple. V equal radical of Vr squared plus V theta squared. So it will be equal to radical of 2 squared cosine squared t plus 2 squared sine squared t. And you will use the rule that gives you cosine squared plus sine squared equal 1, and you will finally find that the magnitude of V will be equal to 2 meters per second. We have now question C. Determine the components radial AR and orthoradial A theta of the acceleration of M. So we need to find the radial acceleration and the orthoradial acceleration of point M. But we have already found V. So here we have two methods to find the acceleration. These two methods are based on the same definition, but we have two ways to make the calculation. So we can start writing a equal dv over dt, and we can make the derivative of the velocity vector, which is given as 2 cosine ter plus 2 sine te theta. So we can derive these two quantities with respect to time. So don't forget that this term depends on time, but also ER depends on time, and E theta depends on time as well as sine t. So while you are making this derivative, so in each term you will consider the rule uv prime equals u prime v plus v prime u, and here you will find a term times dr over dt, and where dr over dt is equal to theta dot e theta, and you will also find dE theta over dt multiplying a certain term, where dE theta over dt is equal to minus theta dot ER. Okay, and you will find the answer. The second method is just to use the rule, which is the acceleration vector is equal to rho double dot minus rho theta dot squared e rho plus rho theta double dot plus 2 rho dot theta dot along e theta. So in this expression, you don't have to make any derivative of the unit vectors with respect to time. Okay, you can use the first method or the second method. Okay, personally I prefer to use the second one in red. We can finally find AR, the radial component of the acceleration vector, equals minus 4 sine t, and the orthoradial acceleration it's equal to 4 cosine t. Now question D, deduce the magnitude of the acceleration vector. The magnitude of the acceleration vector is given by the square root of AR squared plus A theta squared. It's equal to 4 meter per second squared. In question D, they want us to calculate the tangential acceleration AT. AT, well, is given by dV over dt. Let's check the magnitude of the velocity vector. The magnitude of the velocity vector was equal to 2. It was a constant, so its derivative is equal to 0. So AT will be equal to 0. Part F, deduce the normal acceleration AN. So we can use AN equal A minus AT. Where AT is equal to 0, then AN will be equal to A. And it's just 4 meter per second squared. In question G, calculate the radius of curvature rho. Okay, this can be deduced from the previous question. In fact, AN is equal to V squared over rho. So we can deduce rho equal V squared over AN. We know V, we know AN, and finally we will find rho equal 1 meter.